So probability begins with some just general probability rules. The whole first page here is kind of like a little article to explain how we came about with probability itself. So if we think about what we learned in chapter 1 about all of the random processes, a random process represents scenarios where the outcome of any particular trial of an experiment is unknown, but the proportion or relative frequency of a particular outcome is observed approaches a specific value as the number of trials increases. So what we're explaining here, and the very basics of probability you're going to naturally understand. This table is representing the frequency, relative or cumulative frequency, of heads versus tails when you flip a coin. So what's happened here is that the very first time we flipped a coin, we got a tails. So we have a 0% proportion of heads. The second time we flipped it, we got a head. So if we had one head and one tail, it's like they cancel each other out, so we're at the 0 line. So half of the time it's heads. Then we flip a third coin and it's heads again. So that's 2 heads and 1 tail. So 2 out of 3 times would be 0.66 on and on and on. So we're here around 0.6 repeated. If we keep doing this and repeat this experiment over and over, you're going to start to notice that the frequency of the times that we get heads and tails is going to start to become very, very close to 0.5. Which makes sense to us because inherently we understand that if you flip a coin, you have a 50% chance of getting heads, correct? It's either heads or tails. And this is helped, or this is measured probability-wise with this phenomenon of random numbers, specifically when we have outcomes that reveal themselves over long-term predictability. So we can do classical or empirical probability to discuss the different outcomes or probabilities of each outcome. The long-term proportion in which a certain outcome is observed is the probability of that outcome. Because if we had stopped after 2 heads and tails, we'd have said that, or after 1, we'd have said there's a 0% chance of getting a head when you flip a coin because we got a tails the first time. But what we do with these experiments in probability is we repeat them a large number of times so that we even out this random process to what is truly the probability. This probability law is called the law of large numbers. The law of large numbers says that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome, which makes sense. The more often we flip a coin, the more likely our probability-wise, based on what we've observed, is going to be closer to 0.5, since we know you have 2 choices and one of them is heads. I love this petty math fact. So Jacob Bernoulli, who is, he's got a lot of theorems, Bernoulli's theorem. He's an old guy. A major contributor to the field of probability from Switzerland. I love this fact. He believed that the law of large numbers was common sense, and this is evident in the quote from his text from his book. It said, "For even the most stupid of men, by some instinct of nature, by himself and without any instruction, is convinced that the more observations have been made, the less danger there is of wandering from one's goal." So this is something we understood for a very long time and codified into this law of large numbers. Another petty math fact that I wanted to put out there is the fact that you will hear, especially in sports, people talk about the law of averages. That is a fake law. That is not actually a law of numbers. The law of large numbers is a thing, but if you read or hear about the law of averages, whoever's talking doesn't know what they're talking about. The law of large numbers is often interpreted as a non-existent law called the law of averages by folks who misunderstand the law of large numbers. For example, yes? Okay, sorry. So the announcer of baseball says that the guy who's at bat is bound to get a hit because he hasn't hit one yet. He hasn't hit one in a while, so he's bound to get one. That's the law of averages. That's a fake thing, okay? It's a misinterpretation of the law of large numbers. Or in other words, let's say you hear the mother of 4 boys say she is more than likely to have a girl now since we already had 4 boys. In both instances, the confusion is between what happens in the long run, called the law of averages, and what might happen on the next trial of a probability experiment. Given that is you had 4 boys, you're due for a girl with your 5th child, no way. The likelihood is still the same that you get a boy or a girl. Okay, so just make sure you understand this when you're hearing people talk about the law of averages, that that's not a true probability model or a probability experiment. The only thing that's true there is that the law of large numbers means that the more often that an event happens, the more likely it is going to become its true classical probability number. Now, what are those things? Great question. Let's define some words and some terminology that you're going to hear and throughout this chapter so that you know what I'm talking about. In probability, an experiment is any process with uncertain results that can be repeated. So flipping a coin is our experiment. Rolling a dice, that's our experiment. Dealing a hand of cards, that's our experiment. The sample space, which is going to be represented by a capital S, is the collection of all possible outcomes. So if I was making a sample space for flipping a coin, it would be heads, tails. Those are the outcomes of flipping a coin. If I was making the sample space for rolling a dice, it would be the numbers 1 through 6, because those are my option when I roll a d6. An event is any collection of outcomes from a probability experiment. An event consists of one outcome or more than one outcome. We will denote events with one outcome, sometimes called simple events with E subscript of I, but I actually don't naturally do that. In general, events are going to be notated with capital letters such as E, F, and G. Those are the ones you're going to see a lot. So sample space, capital S. Certain events are other capital letters like E, F, and G. If event is impossible, that's a mathematical probability. It says that the probability of the event is 0. That's an impossible event. If an event is a certainty, then that means the probability is 1. I'm going to highlight this in a different color. An unusual event, because that's a true definition right there, is an event that has a low probability of occurring. And in general, we consider that to be 5% or less. That's going to be considered unusual. It's pink. So an unusual event, in general, 5% or less probability. There's parts of this book and then parts of probability where you change that number, but in general, we're going to say 5%. So let's just explore these vocabularies for a little bit. It says a probability experiment consists of rolling a single fair die, which, by the way, a fair die is one in which every possible outcome is equally likely. For example, rolling a 2 is just as likely as rolling a 5. We will contrast this with a loaded die, which is what you want to look out for whenever you're doing things with dice, in which a certain outcome is more likely. For example, if rolling a 1 is more likely than rolling a 2, 3, 4, 5, or 6, then the die is loaded. Okay, so it's weighted differently to roll a certain way. So we're rolling a fair die. If we determine the sample space, I gave this one away earlier, the sample space will be written as big S equal to the set of, so we use the squiggly brackets, please make them look nice. Inside the squiggly bracket are going to be all of the options that I can roll when I roll this dice. And since there are 6 sides on this dice, my sample space is the numbers 1 through 6. To define the event E being roll an even number, what we're going to do is we're going to say that event E is the set of numbers that meet that criteria. What numbers in my sample space are even? That is the event that we would roll an even number, that either we would get 2, 4, or 6 when we rolled the die. So we have sample space, that's everything. We have the event we want, which is exactly how many times that would occur. There are a few rules when it comes to determining whether something actually represents a probability experiment. There are 2 rules that we'll need to check to make sure something actually shows a probability model. When we're talking about probability, by the way, we're going to use this notation PE. We will pronounce the probability of E. So similar to function notation like f of x, this is the probability of E. So the probability that that event would occur. The rules of probability are very simple. Step 1, the probability of any event must be greater than or equal to 0 and less than or equal to 1. So we can't have something have a negative probability. That makes no sense. 0 means it's impossible, so we can't be less than impossible. And 1 means that it's certain, so there's no way it can be bigger than 1, since 1 means it's absolutely going to happen. So we need to check number 1, that all of the probabilities are between 0 and 1, inclusive. The step 2 is that the sum of all of the probabilities must equal 1. That is, if the sample space has the events 1 through n in them, then if we add up all of the probabilities that are listed, all of the probabilities has to equal 1. Otherwise, we're not looking at the entire experiment and all of the possible outcomes, since something is missing there. We need to add it up to 1. That one of those things has to happen because we have 100% certainty that something in that list would add up. If we meet those 2 criterias, then it means that it is an actual probability model. So let's check this first one. We're just going to check and see if the table represents an actual probability model. It says the color of a plain M&M milk chocolate candy can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. Table 1 shows each color and the probabilities of drawing that color. We're going to verify that this is a probability model. So all we need to do is check number 1 and number 2. So for number 1, are all of the probabilities listed in that table between 0 and 1? Yes. So we can say all of them, all probabilities are between 0 and 1. That satisfies the first requirement, that all of those probabilities are between 0 and 1 inclusive. Our second thing is that all of the probabilities need to add up to 1. So let's also try this. If we add 0.13 plus 0.14 plus 0.13 plus 0.24 plus 0.20 and 0.16, if you add all of those up in a calculator, it would need to equal 1 for us to say, yes, this is a probability model. And if you trust me, it does. So since those all add up to 1, you don't trust me, good. Go ahead and type it in. I wouldn't trust me either. Since they all add up to 1, that means that we have satisfied step 2, so we know that, yes, this is a probability model. Thank you. So if you see that and it's wanting you to verify, you check these 2 rules. They're pretty easy to check. Just a quick little check. I'm usually really good at this, but I accidentally didn't put a page break right here. So this is the title of the next page. I know. Well, my copy it printed right and your copy it printed wrong. I'm so sorry. So I thought I was fine. I am not. So on the next page, we're going to compute and interpret probabilities using the empirical model. I would make sure that you have, the box says that title right there, but I would make sure you have the word empirical model written somewhere on this page so you know what I'm talking about when I say something about the empirical approach or the empirical model. The empirical method gives us an approximate probability of an event by conducting the probability experiment. So we're actually going to do the experiment, and we're going to see the probability is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So this is what happened in that first graph on the very first page with the heads and tails experiment. We were looking empirically, actually running the experiment, to see what we would actually get each time we flipped the coin. So our probability of E is the relative frequency of E, meaning the frequency of E divided by the total number of trials of the experiment. So if I got a heads 5 times and I flipped the coin 7, this would be 5 out of 7. So out of 7 trials, I got heads 5 times. That's the sort of thing we're doing here. So in example 3, let's go ahead and try it. It says an insurance agent currently insures 182 teenage drivers from 16 to 19. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on these results, the probability that a teenager will file a claim on his or her auto policy in a given year is, here's how we write this. We will say the probability that the event a teen files a claim will be approximately equal to the relative frequency. So how many times did we see that? Is that the lunch one? No, that's the warning one. How many times did we see this last year? 24. Out of how many drivers? 182. So 24 out of 182, go ahead and throw that into a calculator. You're going to give this to me as a decimal. 24 out of 182. 0.131. Yes. So 0.13, we'll go and write that to 2. So that tells me that about 13 out of every 100 teenager will file a claim, or about 13% will file a claim. Okay, so it's number of times it happened out of total number of trials. Okay, let's see from survey data how to build a probability model. The data in the table represent the results of a survey in which 200 people were asked their means of travel to work. We're going to use this survey data to build a probability model for means of travel to work. Now, because I know we're going to do this probability empirically, and I've done the experiment, I need to know how many times I've straight up done the experiment. So I need the sum of this entire row. Now that we know the symbol from the last chapter, I'm going to keep using it. So this is just adding up all of the frequencies, which is how many? 200. So we surveyed 200 people and said, how do you get to work? And here's how they answered. Now the probability of each of these is going to be the frequency of that event over the total number of trials. So the first one will be 153 over 200, which if you calculate in your calculator is 0.765. We do this for every row, which means we do the carpool row, 22 out of 200, I wrote 100, LOL, which would be 0.110. 10 out of 200 for the public transportation. And just kidding, we will finish this after lunch because that's the lunch bell. Oop. Once we have all of the probabilities, we need to verify that it is a probability model, just because that's good work. So question for you, are all of the probabilities between 0 and 1? Good, so that's the first rule. The second rule is that all of the probabilities add up to 1. So in your calculator right now, can you add all of these probabilities for me so we can verify that the sum of all of the probabilities is 1? Okay, fabulous. So we know that this sums to 1, which is what we wanted. We have verified that it's a probability model. We're going to then estimate the probability that I randomly selected individual carpools to work. So using the model, we're going to say the probability that somebody carpools, that's the event, is that they carpool, is simply 0.11. Or if we were to survey 100 people, 11 of them would carpool to work. 11%. Question C says, would it be unusual to randomly select an individual who walks to work? Okay, well, the probability that an individual walks to work is 0.025, which as a percentage is 2.5%. Now remember, to verify that something is actually unusual, there was that percentage we were going to use. What did I tell you to use to clarify if something is unusual? 5%. So is 2.5% less than 5%? Yes. So that means that, yes, this is unusual because 2.5% is less than 5%. So we are officially considering it unusual that somebody walks to work. Yeah, so the definition on the page before this, we're considering something to be unusual if the probability is less than 5%. So since our probability of walking to work is 2.5%, 0.025, then yes, it is unusual since this percentage is less than 5%. Now that was the empirical method, the empirical model. We can also do probability and computing and interpreting them using the classical method, which is probably what you are more used to seeing when it comes to probability. This comes from when we are observing events that have equally likely outcomes. meaning you're not using a loaded dice, you're not stacking the cards, you really are shuffling them, those sorts of things that have an equally likely probability of happening, equally likely outcome, not probability of happening, I said that wrong. So if we compute probability using this classical method, if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E is simply the number of ways E can occur over the number of possible outcomes. So we got all of these formulas, but what I really want you to focus on is this one. The probability of an event is equal to the number of times that event can happen divided by the number of items in the sample space. So the number of times the event could occur divided by the number of items in the sample space. We're going to hop right into it. Let's say a pair of fair dice is rolled. So we roll 2 dice. Fair dice, remember, are where they're equally likely. It's not a loaded dice. Here is the sample space. So this is S. We rolled 2 dice. We could get snake eyes. We could get 1 and 1. We could get 1 and 2. We could get 1 and 3. Do you see how this is telling us the sample space? The options that could happen if we roll the 2 dice. This is all the combinations of outcomes we can have. So a question for you, what is the number of items in the sample space? Six rows, 6 columns. How many items? 36. So there are 36 different outcomes that you can get when you roll a dice. It says to compute the probability of rolling a 7. So if we're going to do probability of event E, which event E is going to be defined to be the probability of rolling a 7, we need to do the number of times you can roll a 7 divided by the number of items in my sample space. So we need to look at our entire sample space for the number of times we can roll a 7. Here's a 7, 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 and here's a 7. How many options do I have, combinations, that would roll a 7? There are 6 number of times that we see a 7 in our sample space out of how many numbers in our entire sample space? 36. So our probability would reduce down to 1/6. So you have a 1 in 6 chance of rolling a 7 when you roll 2 dice. So it's the highest probability that you would get because the rest of the combinations are different. Let's do this again, but let's compute the probability of rolling snake eyes, which means that you're rolling a 2, okay? So if we do this, we're doing the probability. This time we'll use event F since these are different events. And so we're going to count the number of times we can get, we can get snake eyes. That was the cutest little sneeze I ever did here. Over the number of items in the sample space. So this is snake eyes, number of snake eyes that we would get over the total number. So how many ways can I roll 2? There's only one way to roll the number 2. So my probability would become 1 over the number of items in the sample space, which is 1 over 36. You have a 1 in 36 chance of rolling snake eyes. So if we compare these, rolling a 7 is how many times more likely as rolling a 2? It's 6 times as likely. Like, what would you have to multiply it by? To get 136 into 636, you'd have to multiply it by 6. So it's 6 times as likely that you'll roll a 7 than if you'll roll a 2. This is the odds of rolling a 2. This is the odds of rolling a 7. This is 6 times. I know we reduced the fraction, so it made it a little harder to do, but if we go look at the common denominators, 6 times as likely. Okay. So this little tidbit right here is pretty important. We just saw that the classical probability of rolling a 7 is 1 out of 6, which is 0.16 or 0.17%. Suppose a pit boss at a casino rolls a pair of dice 100 times and obtains 15 sevens. This is an empirical probability problem now because we're actually running the experiment. We would assign the probability of rolling a 7 as 15 out of 100 or 0.15. If the dice are fair, we would expect the relative frequency of 7s to get closer to 0.167 as opposed to 0.15 as the number of rolls of the dice increases. So we rolled it 100 times and empirically saw that this happened. If he keeps rolling the dice, our fraction is going to eventually get very, very close to the classical probability model. In other words, and let's highlight this because this is very important. In other words, empirical probability will get closer to classical probability as the number of trials in the experiment increases due to that law of large numbers. So if we just rolled the dice 2 or 3 times, we probably wouldn't get very close to the classical probability. But in our empirical model, if we roll that dice a lot of times, it's going to get closer to what we classically know will happen with the different die rolls. If two probabilities do not get closer together, we may suspect that the dice are not fair. So this is how they check to make sure you're using a fair die. Now, applying this to some other examples we've done previously in this course, we spent a lot of chapter 1 talking about simple random sampling. And if you remember from when we talked about simple random sampling, each individual has the same chance of being selected, which means we can apply this to classical probability since every opportunity for the person to be chosen has an equal amount. Now, we've seen this example before, I think in chapter 1. It says Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. So to be fair, Sophia randomly selects the 2 people who can go with her. We're going to start to talk now about the probability of these things being chosen. So first things first, we have to determine the sample space for the experiment. So we need S, which means we need to list out all of the combinations of friends that Sophia can bring, which would be choosing Yolanda and Michael, or Yolanda and Kevin, or Yolanda and Marissa. Deal with it, it's fine.
No, I don't want to.
We could also combine these in different ways. She could pick Michael and Kevin. She could pick Michael and Marissa. Or she could pick Kevin and Marissa.
Okay, I'll think.
That's it. We're just choosing 2 people out of a list of 4. Well, let's see. What is the number of items in our sample space? 6. So if we look at the classical probability here, the event we're looking for this time is that Michael and Kevin attend the concert. There is only, following the probability model, the probability of E that Michael and Kevin are attending the concert is the number of times we see Michael and Kevin get chosen out of the sample space, which, yes, is 1 out of 6. That makes sense. But let's say we compute a different probability, and this time we're computing the probability that just at least Marissa gets to attend the concert. Go, Marissa. Okay, so let's do the same thing. This time we're going to use F to represent the event, and we're defining it by color here. We're saying F is Marissa attending the concert. So question for you, how many times on that list is Marissa's name there?
3.
I see Marissa's name on my list 3 separate times. So there are 3 ways that we can choose people, and Marissa would get chosen. So the number of times I see the event F happening is 3 out of my sample space of 6, which means Marissa has a 50-50 shot of attending this concert. So if we extend this beyond just this little interpretation right here and kind of explain how this applies to large numbers, if we conducted this experiment 100 times, how many times would Marissa attend the concert? Yeah, 500 times. Yeah. Did I say 100? Oh, my bad. 1,000 times. I can read. If we conducted this experiment 1,000, I guess. Not too sure. Yes. So we define the different variables to represent different things. So F for me means Marissa attends the concert. It's not like, so really what I should have done is said that the event F is Marissa attends the concert.
So can I put an A if I wanted to?
Sure. Because the word event starts with E, we generally do E, F, and G, just following those letters in the alphabet. But that's essentially what I'm doing is I'm defining the event E to be these different things. Thank you for asking. Let's see another example here.
We have choice.
Classical and empirical, we're going to combine them together. Suppose in a survey that we ask 500 families with 3 children to disclose the gender of your children and found that 180 of the families had 2 boys and 1 girl. Using the empirical method, we're going to estimate the probability of having 2 boys and 1 girl in a 3-child family. Empirical method means we're actually using the survey data. So actually using the survey data, the probability of E, and E being that we have 2 boys and 1 girl, so the probability of E is going to be the relative frequency of E, or the number of times I saw E happen in this experiment, which how many times did that actually happen? 180 times. Out of how many families did we survey? 500. So if we do this math, that's going to give me 0.36. So by empirical evidence, we have a 36% chance of finding a family with 3 children where there are 2 boys and 1 girl. But let's do this now classically. So not looking at the survey data, but thinking in general, classically, about what could happen here. To do this, we need to define the sample space. So to do this, let's just start off with a family of 3 boys. So I'm going to say B, B, B. That's for 3 boys in a row. I could also have a family that had a boy, then had a boy, then had a girl. You see what I'm doing here? I could also have a family that had a boy and a girl and a boy. Or a boy and a girl and a girl. Or I could have a family that had a girl first and then 2 boys. Or a girl, a boy, and a girl. Or a girl, and a boy. Or all 3 girls. There's the sample space. These are all of the options of combinations of boy and girl in 3 kid families.
This is writing capital G so much it looks like arrows.
What's up? Order matters. Yes, I know what you're saying. Like there's 2 B's and a G.
Like say nothing about like in order, like that's what I meant.
We're gonna allow order to matter. We'll talk about more of those counting techniques later in this chapter. So my question for you is, what is the number of items in the sample space?
8.
8. Now, what is the number of times we see our event occurring? Remember, our event is that there is 2 boys and 1 girl.
Once.
Are you sure? I see 2 boys, 1 girl here, 2 boys, 1 girl here, 2 boys, 1 girl here.
Those 3.
So 3 times. I see this occurring 3 times. So if we go to compute our classical probability, our probability of event E, that we have 2 boys and 1 girl, will just be the number of times we see that occurring over the total number of in our sample space, which you guys told me was 8. So this would actually be 3 out of 8. And if we make that into a decimal, that's approximately, actually I think it's exactly 0.375. Check out those numbers. From empirical evidence, we got 0.36. Classically, we got 0.375. If we surveyed more than 500 families, if maybe we surveyed like 5,000 families, this number would get closer to this classical number due to the law of large numbers. So we can do probability either way. If you have empirical evidence, meaning you've done the survey, you're doing empirical probability with frequencies. Or you can think about the entire sample space in general and do classical probability. Yes? Fabulous.